Welcome. So in this lab, we're going to be looking at the properties of light in two different ways. We're going to look at the properties of light via emission and the properties of light via absorption. We can split this into really three major parts. The first part we're looking at light emitted through electrical excitation, and then looking at the line spectra of how this splits apart when viewed through a prism. The second part of this one is we're going to excite these metals through fire. We're going to use fire to excite them and produce various colors. Then finally, for the last part, we're going to look at the absorption spectra. Not what light do they emit, but what light do they absorb to produce the colors that we see. And that one will lead us into the experiment for next week, which is our Beer's law, colorimetric absorption. We're going to look at how light absorption is a function of concentration. So that's not till next week, though. We're going to just barely scratch the surface by looking at the absorption spectrum. So that's what our plan is for this. We'll be breaking down into lots of short little videos and pictures, essentially showing what this looks like. The first thing you should know as you look at the prismatic the image through the prismatic glasses is that you see multiple images of the light being refracted into its various wavelengths, going through the Voigt-Biv spectra, but in reverse. So violet is closest to the light, and red is farthest from the light. And if you were to see further images, they'd start repeating again as you get further and further away if images are intense. So what you're going to see is a series of gases. First, we're going to see the gases without the glasses to see what underlying light. Then we're going to see the light with the glasses, and you'll see first a very intense spectra closest to the light. But if you start seeing it again, it'll repeat again. This will be like violet through red, and then violet through red again. The second spectra was showing the principal colors that the light is made up of. So the first one might show all of the colors, but the second one, as they decrease in intensity, shows just the ones that are the most intense, the main components of the light. You should probably look to that one to better get a feel for what the light is made up of. Same ionization of copper. flame ionization of barium. Let's see if I can do that again. Flame ionization of potassium. Do that again. Flame ionization of calcium. One more time. Flame ionization of calcium. One more time. Flame ionization of sodium. One more time. I am redoing one of them as an unknown. See if you can determine which one this is. Which of the metals is this? At this point, we need to calibrate our spectrometer. So we're going to fill a cuvette like this with deionized water. Make sure there is no air bubbles. Completely wipe it out. We want it to be just a column of water. What this is going to do as we calibrate, it's going to take whatever absorptions the solvent would normally make and set that at 0. From there, we are essentially zeroing out so that everything that gets absorbed is our sample. Most of the time you can skip the warm-up phase, but if you really want to, you can wait like the minute and a half. But I know I've already waited well beyond that minute and a half. Hit the finish calibration, hit OK. And now I'm ready to add my sample. Do a sample with 0.1 molar copper. Note the color. So I'm going to fill my cuvette with a small amount of my sample just to coat the sides. Dump that into the waste and then fill it up and wipe it down. And then I'll start it. I want to make sure there's no air bubbles. So that went. All right. So you'll see a full spectra over here. Full spectra of the whole absorption, and you'll see it's absorbing So it chooses the maximum wavelength, but you can see the blue, green, red. See, it absorbs in the reddish region, reddish orange, but the wavelength max is at 844.6, and the absorption is 1.797. We're going to dump this out and repeat that with 0.1 molar cobalt. Note the color. So we are going to, I'm going to squirt a little bit of cobalt into my cuvette, dump it out into the waste before filling it properly. Trying to remove as much as our last solvent as possible. Trying to bump any air bubbles out. Air bubbles absorb differently from water. Thus, we'll have a different spectra if we do that. Sorbine. So, notice it seems so small, but as soon as I hit stop, it's going to change it. So we have a wavelength of 507.3 and absorbance of 0.511. Ready to continue with our last one is 0.1 molar iron. Notice that the bottle is pale yellow. It's kind of hard to tell otherwise what color this is because it's not a very bright color the same way as our cobalt or copper, but it is still a colored complex. One last time. Absorb, absorb, absorb. And there's our, we have a wavelength of 386.8 and absorption of 0.241. So, notice where it absorbs at. Notice where it does not really absorb at. That is related to its color. And now we have everything we need to calculate both color, color absorbed, color transmitted, energy of light absorbed, and molar absorptivity. So as I said, there's not many calculations you need to do just based on this last part. This was a fun lab. This was an easy lab. It's a shame you guys missed out. Maybe next semester come on by and we'll do some more flame emission stuff. It's pretty fun. It's essentially the same chemistry behind fireworks right there. So you need to turn wavelength into energy, into frequency and energy, and you have to turn absorption into molar absorptivity using the concentration. Those should not be too hard, shouldn't take you too long to do. Good luck. I'll see you for the next lab.